So, Dr. Dinesh Manandhar, he is bachelor's in electrical engineering from Punjab Engineering College, Chandigarh, India, and master's from Asian Institute of Technology, AIT, Thailand, and PhD from the University of Tokyo, Japan. Dr. Manandhar is an associate professor at the University of Tokyo, Japan. His research work includes indoor navigation, GNSS signal analysis and design, jamming, interference, and spoofing, which are very new topic and very interesting topic, detection and mitigation. He is currently working on GNSS signal authentication based on QGSS signals. He has also developed IMES, indoor messaging system based on GPS for indoor navigation. And I have no hesitation in saying that with his kind help, support, and obviously training, our group, we started working on the small modules, GNSS small modules. At least I learned these things first from him. And once again, on behalf of all the participants and the organizers, we welcome Dr. Dinesh Manandhar and welcome to deliver his lecture. Dr. Manandhar, the floor is yours.
Yeah, thanks, Anindya. So thank you very much for introduction. Okay, so, let me start straight. Uh, do we have to wait a few more minutes? Do you think more people will join, or should we start? Hello?
I was muted. So you please start. So let the people join.
Okay. 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 I think I need to put this in the slide mode first. Um, okay, can you see my slide in presentation mode?
Yes.
Okay.
Yes, we can
So
see.
I have two presentations today, one for low cost receiver systems and the other one is on spoofing. Uh, Actually, the time allocated is, I think, 3 hours or 2.5 hours, but I would like to finish maybe within 1.5 hour. So I would like to make it very compact because of the time. Um, Maybe within 1.5 hour at the most. I think we can do that. So let me present about low cost receiver system first. So my slide, I will share this slide with you. It has so many slides. The file has so many slides, but I will not go through all because I think during these few days you already heard all of these things. But I will probably focus some few other slides which probably might be new to you. So I will skip these things, okay, because these are not necessary for you because you already heard so many things in the from previous trainings or lectures, or you already know about it. So I'll skip these type of slides. I'll skip this. And I just want to let you know that new systems are coming up from Korea, Korean augmentation satellite system, and also they are coming up with a new navigation system. And and also the Australia and New Zealand is going to have their own SBAS system. And Nigeria, they have it, but it's not. I don't think it's functioning regularly. And Algeria is coming up as well. And if you look at some software like a UCenter for UBlocks, so what I wanted to highlight is that even the very low cost receiver system, you will see so many signals here. Okay, So here you can see GPS, S-Bus, Galileo, Beidou, QZ, GLONASS, and the Navic or IRNSS, because in the beginning IRNSS was the name, then it was changed to Navic now. It's not yet compatible, but I think it will be compatible uh, in future. Yeah. But anyway, so we see so many signals here. So this is what Aninda introduced about my work, IAMS, indoor messaging system. Actually, UBlocks, this receiver is compatible with the IAMS signal as well. Uh, if you have a IAMS transmitter in your location, you can receive it, but this has to be installed by someone else. So this is my one of the signal design here for the indoor navigation IAMS. Okay. So this is you can also see some message types of IAMS in the settings. Um, and if you look at the more detailed settings for the low cost, if you have a dual frequency receiver like F9P, and you can individually enable or disable the signals for L1 and L2 or E5B. Actually, the module is designed for L1, L2, but the L2 front end is designed with a little bit wider bandwidth so that it also cover E5B signal, which is the Galileo. So it's very smart design of the front end so that with dual frequency, you can cover three different frequencies, okay? L1, L2, and L5B, E5B. So this is what we can set up in F9P for a dual frequency low cost receiver. And F9P is very widely used in many high accuracy applications. For example, UAVs or drones that requires high accuracy for direct georeferencing or accurate navigation of the UAV. Anyway, so you can do all these type of controls now. So it's getting very, very powerful, although it's a low cost system, and the accuracy is very much comparable to high-end receiver systems. There's no compromise on in the accuracy. Okay? And these type of low cost receiver systems, although it's low cost, those that are designed for high accuracy for the carrier phase data to do the RTK or PPP, so it outputs pseudo range and carrier phase and Doppler. So all the informations, all the data that are necessary to do the RTK or carrier phase processing. Okay. So if the receiver can output this type of raw data, we can do RTK or PPP or high accuracy data processing. And so these are the requirements. And at the same time, if you see here subframe data, so this raw data is coming from the raw message from this sentence, but also we can get the navigation data bits itself that's coming from the subframe data. Okay. Now the question is, how can we improve the accuracy? And I suppose that you already know this, but let me just show you a few slides. So our basic problem is that when we log the data, like you have any standard, I mean, observation with the GNSS receiver. For example, you have a very costly receiver, $10,000 Trimble Net R9 receiver. And if you log the data for few hours, and if you plot the error, the scatter plot of X and Y, you will get something like this. And this will give you a standard accuracy of few meters. Yeah. So it doesn't matter whether the receiver is a $10,000 or $100. You will get something similar. Maybe $100 is more, worse than this, but still, even the expensive receivers, high-end receivers, doesn't give you a centimeter without removing some errors. Yeah. So the thing is that in order to have centimeter level accuracy, we must remove the errors. Yeah. Then we can get high accuracy. And there are different ways to remove the errors. We need to do data processing to remove those errors, either in real time or in post-processing mode. And there are different ways of doing this, and there are different ways of observing the data. For example, this is the standard point positioning without doing any differential correction. That means we connect the antenna to the receiver, we put on the power, we log the data, we output the data. That's all. And then we have a differential correction, differential GPS, and it's done based on the code phase observation only. And in this case, for the differential correction means we need a reference station. So we should have a base station or a course station, and then we have our field unit or the rover unit, and then we get the correction data from the base station. And that correction data may be only related with the code phase observation or both code and carry phase observation. So if we want to do a simple DGPS, then code phase observation is okay, pseudo range is okay. Then we get this type of blue dots. And here we get accuracy of a few meters. Okay, 1 to 3 meters of accuracy is possible, or even sub-meter is possible. But still, it will be like this. But if you take a mean from this, you get a very high precision. Okay, so the standard deviation will be you can compute the mean and standard deviation from this, so it will be a very nice value. But the point is that you are observing for a long time and you take a single mean. But if you are moving in a dynamic, so you have only one epoch, that means you may have that one epoch either here, that one single epoch may be anywhere between here to here, okay, or it may be here. If it is here, it's okay, but if it is here, you have a big error. That means this accuracy is now this about plus minus 1 meter. Okay, this is 50 centimeter grid, so we'll have about 2 meters error or 3 meters. So with DGPS, we can say that okay, we can guarantee that we'll have accuracy of 3 meters or plus minus 1.5 meters. Yeah. So something like that. Anyway, but it will be like this. It's a very nice randomly distributed points here. And I'm showing here with the same data. So these blue data were calculated from these red dots, okay? Blue dots from red dots. And then if we do the carry phase observation computation, then you can have this type of green dots. So you will have a centimeter level of accuracy. But to but in order to get this level of accuracy, we need to have a carry phase observation. That means we need to have a pseudo range carry phase output from your rover, and also your base also should be able to provide all these type of observation data plus some other informations. Then we can have this level. That means we need to have an extra setup for this, and that's additional cost. But the problem is that how can we go from these red dots to blue or green dots? Okay, probably blue dots is enough. This type of DGPS is enough for many applications, but some special applications may need these type of very high accuracy green dots. And when we do the training, so these slides are from my GNSS training slides, and we provide a sample data so that the participants they can process the data. And for example, they do the single point positioning, and they will have this type of output. And for the same data, they will do the DGPS. Okay. And then again for the same rover data, they will do the RTK, and they themselves see how these red dots will change, how the red dots change from this type of scattering accuracy level to blue ones, and then finally to the green ones. Okay, so the accuracy improves from few meters to centimeter level. So the participants can see themselves, they will process the same data and get different types of results so that they can understand how the errors are removed by using the different types of data processing techniques. Okay. This is what we teach in our training. And when we say low cost receiver, so there may be many different types of definitions. So this is my definition that I use for low cost. When I say low cost, means that it should provide a sub-meter level accuracy. I'm not saying it should provide a 5 centimeter or 10 centimeter. My accuracy is sub-meter. For example, even a 70 centimeter is okay, 30 centimeter is okay, 50 centimeter is okay. But also the size is no, the weight must be very small, and the price is less than $100, okay, or within $100, including everything, antenna, receiver, or whatever is necessary. So this is my size. So 100, 100, 100. Okay, $100, 100 centimeter accuracy, 100 weight. These are my comments, not the size. Sorry. And then we go to the decimeter level. So if we go to the decimeter level, then maybe the cost is a bit higher. so about $300, less than 300. Or if we go to centimeter, maybe it's even higher, maybe 500, but I want to fix within $300. So if you look at this, the price should be within $100 to $300 and shall provide a sub-meter level of accuracy, and the weight and everything must be small. So when we fix the price, low cost, so you look at the price here, the price tag is $100, means you can't use a computer because computer is quite expensive. So we should avoid the use of the computer to log the GPS data or to use the GPS data. The receiver itself must be able to do all the processing that are necessary to provide this level of accuracy. This must be possible to do. So these are the requirements. And now we are trying to do this. And so far we have come here, but this price tag is a little bit higher, about $500 at the moment for this 10, 20 centimeter accuracy. But for this one, we can have it within $100, no problem. And why we can have such a high accuracy is very simple. You probably know this because the satellites have orbit error and clock error, so they always present. And also ionospheric and tropospheric effects are always present. Multipart we can't remove. Okay, it will be there, and it's variable. It can't be modeled as well. Some very small, large multipart it can be removed, but small multipart is quite difficult to remove. And the receiver clocks will be, of course, it will be removed while doing all these pseudo range computations and all. But if we can remove these errors, so we can improve the accuracy. It's a very simple logic. So you remove these errors, you reduce these two errors because we can't remove ionospheric and tropospheric errors. And this is a table showing that which errors can be removed and which errors can be reduced. These are just some sample figures, so don't take it as an exact value, just a tentative example that how much error can be removed. For example, satellite orbit and satellite clock errors can be removed completely, okay, by doing the differential observation or differential correction. It may be DGPS or the RTK. And then ionospheric and tropospheric can be minimized from few meters to less than, I mean, few centimeters, I mean, few tens of centimeters level. So that's how we can improve, but we need to do the differential observation or differential correction. Now, the problem is how to do the differential observation or differential correction. Okay. So this is what we do or what everybody does. You have to put a reference station at a known point. Okay, so this point must be surveyed first, or point must be known. The XYZ coordinate must be known, and then you also observe the GNSS measurements here for all the visible satellites. So since this coordinate is known, so you can compute the measured value here, and then you know the error here. Okay, and we use this type of information, the observation data here, and send this type of observation data to the rover so that the rover can use this type of error informations and do some mathematical computations to remove the errors here. Okay. So this is what we need to do. Uh, the thing is that this type of base station has to be established or set up at certain distance from the rover. So the recommended distance is that it should be within 30 to 40 kilometers. Okay. If it is very large, far from here, the mathematical, I mean the model, the space weather or the condition over here in this space, and this will be quite different. So we would like to have the same atmospheric condition or space weather, space condition here. So that means the distance between the two receivers should be within certain limit. That's, I think the recommended is about 30 kilometer. That means at a radius of 30 kilometer or at a diameter of 60 kilometer, you should have one base station. And if you want to serve the whole country, like India is huge, I think India needs, I don't know, they estimated around 3,000 or more this type of base station. So you have to establish more than 3,000 stations all over India to have a very high accuracy positioning service. Okay, and to operate, to install, to set up, install, and operate and maintain those 3,000 to 5,000 base stations is extremely expensive is extremely difficult. Okay? Of course, it can be automated, but you do need the the huge cost to do the operation and maintenance. Okay? But if you can do that, then you can provide centimeter or decimeter level 10 20 centimeter of accuracy all over India, and that will benefit the huge infra like a railway system. So that's the huge infra of railway and huge infra of the transport systems, all the cars, trucks, all these vehicles, and UAVs, the aircrafts, and the marine is used. So compared to the applications that will benefit, I don't think the cost of this base station for 3,000 will be that expensive. But it really need to be. It's really a very challenging work job to operate and maintain in more than 3,000 stations continuously in real time. Okay. Um, but there's other ways to do like PPP, Madoka PPP, like what Japanese satellite is doing. Now, instead of doing broadcasting from the this type of base stations, you can also broadcast the same correction data from the satellite itself. Okay, so what we are doing is you will just broadcast the satellite orbit error and clock error from the satellite itself instead of using the some ground-based network. So you don't need the base stations in this case. Okay? But what you need is you need a separate signal or separate channel to send the data from the QGIS satellite to the receiver, to the rover. And this is done in the case of QGIS by using L6 signal. We call the L6 band, and the signal name is called Madoka. Okay? And this provides about 10 to 20 centimeter of accuracy, and this can be used globally. Yeah. This provides the correction data for GPS, Galileo, GLONASS, and the QGIS. So if you are using GPS, Galileo, and GLONASS for your position computation, you can remove the errors and have accuracy of 10 to 20 centimeter. But at the rover side, you still need a dual frequency receiver here to do the ionospheric correction. And in Japan, we already have the very large number of course or base stations, about 1,300 stations. So in Japan, they use those already existing base stations to provide also the ionospheric and tropospheric correction data through the satellite, and that is called the CLAS. Okay? And this CLAS gives 2 to 5 centimeter of accuracy, but this is applicable or available only for Japan. So if you want to do outside of Japan, then also we need to have a large number of base stations, but that will be in that case, it will be very much similar to the RTK service. Okay? So anyway, I think Madoka is quite good enough. So you can also use the Madoka PPP in India. And now we have developed different types of low-cost receiver systems for RTK and Madoka, and we have a different versions of Madoka as well. RTK Droid means this is to be used with Android device. So you use Android device and connect your receiver to your Android mobile phone or tablet, and you can do RTK. So this is Madoka using the Android device, and this Madwin is Madoka using the Windows for computers. As I said, if you use computer, it's no more low cost for us, but for development and doing some tests, some field surveys, sometimes we have to use a Windows-based system as well. But yeah, we have this one. But anyway, our target is this Madroid or MadPi. MadPi is a Madoka using the Raspberry Pi, okay, like this one. So this is a very small Madoka receiver, L1, L2, L5, L6 receiver, and the very small here, the Raspberry Pi, and put antenna on a tripod, and you do the observations, and this gives you accuracy of about 10 to 20 centimeter. You don't need any base station. Okay. Now, let me skip this one. Now, the question is how to make a low-cost GNSS receiver. Okay, so there are many different ways to do this. So to make a low cost, you need a module, not a receiver. I mean, a receiver with a box. That will be expensive. Okay? For example, you buy a UBlocks MAT or F9P or Mosaic these devices. Now it comes with a board, a handy board that is easy to use. So you can buy those boards, not the module itself. The board you can buy, and this F9P you can buy a board, and then you add you need to add microcontroller or microprocessor to do the RTK or to do the Madoka PPP. Okay, so you need to have some microprocessor or microcontroller, and then to log the data, you need a memory, either a SD card or a interface port to the hard disk, external hard disk. Okay, using the external interface. So you have to create some interface port, need to add a controller, microcontroller, or microprocessor, and then you need some memory, internal memory, if you want to log the device, log the data into the device itself. Okay, and it can be many different types of things. And those type of, for example, in the memory, it can be just a micro SD card or this type of pen drive or hard disk. And your single board computer or microcontroller or microprocessor can be either Raspberry Pi, Arduino, just to log the data, it's enough. If you need to do RTK, probably you will need the Raspberry Pi or a little bit high capacity CPU should be used. But Arduino is enough just to log the data without doing the processing in real time. For example, if you are going to do only post processing, so just connect this board to the Arduino and log the data using the Arduino to the local drive, I mean local memory. Okay? And you need some other things, may need other additional things. Okay? And also, we are using ESP32, this microcontroller. It's very powerful. It has a Wi-Fi Bluetooth already, and some ESP32 evaluation kits come with the SD this slot as well. So you just buy that type of board with the SD card slot, and you connect this module to the ESP32 directly, and then you can, if you want, you can do the real-time processing, or you can just log the data for post-processing. And if you just want to log the data for post-processing, I think it's very simple. Just need to connect few wires and do a little bit of some interface programming. And many sites, they provide sample codes to do that. Okay. And also it has a Wi-Fi Bluetooth. Then other way is that if you don't want to do any programming, so then you can just send the data through the Bluetooth to your Android device or to your server somewhere, and then you do all the processing later at the server side. Okay. So there are various possibilities, and you can do it in many different ways to make it the whole system low cost. And actually, we started this type of development cycle when we had the first UN Nepal GNSS workshop in December 2016. Because when I started doing this type of GNSS technology promotion in Asia, I found that the receivers were quite expensive. So in the beginning, we purchased the more than, I mean, 10 units of receivers, and each unit cost us around $15,000. Okay, with big antennas, receivers, and so many things. But the problem of those things were that they were quite good, but it was not good for training. We can't carry those type of expensive and heavy equipments to do the training. And even if we carry, it's just one unit, and that's too trouble to carry from one country to another country. You can't even take it. Okay, I practically found it useless. Okay? Those expensive things. It's good only for observation, static observation. It's not good for training. It's not good for capacity development. You can't use it in the classroom. And even if you have it, so you have to request it, and if you may afraid of getting it lost, getting it damaged, it's so expensive. So that's not, I don't think that's a way to good way to do the teaching and promotion. So what I thought is that, okay, why not to use the low cost? But the problem of low cost at that time was that we didn't know how to make it high accuracy. So we didn't even know whether it can be high accuracy. Yeah, but we started testing and making it and integrating and doing several things, and we found several informations that it's possible to do that. And what is more important is the software. But the software was already developed in Japan, RTK Live, which is very quite used around the world. So we had access to RTK Live, and also we had access to all these bugs and all information how to correct and all, because the developer was also from Japan. He's also from Japan, so we have a direct contact. So that help us to integrate this type of low cost system. And then we tried with the single frequency UBlocks MAT, and from there we went to dual frequency, and then we went to Septentrio, and then we went to other modules, and then we changed from computer to Raspberry Pi, then to Android, and so on. And now it's we had a very nice system and very compact system. So this is how our Android-based software looks like. It's very nice and easy to work. So you just connect some few cables, and that's all. Yeah. And now we are exploring how this low-cost system can be used for different types of applications or new applications. Of course, we did the high accuracy positioning system, and then we did this high accuracy using RTK. We did high accuracy using the Madoka PPP, and then we integrated with the Android device. Now we are exploring how this can be used for space weather, because space weather requires huge raw data at a high data output rate, and we don't know whether this is possible. We are exploring at the moment. And also we developed some applications based on the low cost system. For example, monitoring the city air quality, dynamic air quality. You put the device on the vehicle and observe the air quality dynamically, okay, continuously. And then this is our target for 2022, 2023. We start the space weather and air quality we did last year, and also we are improving on this. And then, oh, sorry, we want to know from you, what do you want to do? Maybe some new idea or something you want to do. We'll also think up, and we'll probably upgrade our system. And this is all our system that we did in the past and how we did it. For example, you can connect the GNSS receiver to Raspberry Pi Zero. That's a $12 this board, and this is about $40, $50. There are different modules you can use. So within less than $100, you can make a very nice data logger. And but you have to do the post processing. This is not enough power to do the real time RTK. If you want to do real time, you need a Pi 3 or maybe Android device itself. But unfortunately, Raspberry Pi 3 is not available at the moment, so it's quite expensive. The products are not available. And this is how our Madoka, the Madoka PPP for high accuracy, looks like. We have a MatPi, so this is the antenna, and we have a Madoka receiver, which is shown here. It is very small, 6 centimeter by 6 centimeter size, and you connect this by the USB cable to this Raspberry Pi 4 device, and this device has a touch screen. So that's all. Okay, you just connect this antenna to the receiver, then connect this receiver to the Raspberry Pi by USB cable, and then put the power on, and it will you have the menu pop up, and then you select what you want to do, and this will give you everything. And if necessary, you can also send data output data to by Bluetooth link to some other system, okay? Because Raspberry Pi has a Bluetooth, and you can send this output data using the Bluetooth to the some other system. And the same thing, the Madoka, you can also connect to the Android device and use your Android mobile phone to log the data. So the purpose we did for Android is because many people have a smartphone, Android device. So then you don't even need to buy the Raspberry Pi, because Raspberry Pi itself costs another $100, okay, $60, and plus you need the touch screen plus other accessories and all power supply units and so on. So if you can use Android, so we can reduce that $80 at least. We can minimize $80, because this device you already have. We assume that you already have this device. So you just need this OTG cable. Okay. Unfortunately, so these two systems, the Madoka PPP is not working now because the QGSS has changed the navigation data format. So we changed the format from SSR to compact SSR. And at the moment, we are developing new version of Madoka PPP. So we need to upgrade for the new signal to be compatible, our receiver system, our software. So it will take some time, maybe about another 1 or 2 months to upgrade our previous software. then we can use this system again. And this is a very simple, I think you saw this many times, or maybe you are working on this using the UBlocks. Okay, I will skip. I will skip. These are just the screenshots for RTK and Madoka. And this is a little bit about how Madoka system works. Uh, okay. Also, I mentioned before that Madoka provides the correction data, orbit and clock error correction data for GPS, GLONASS, and QGSS. Okay. So all these correction data are broadcasted by using the Madoka signal. And if you have a Madoka receiver, so you can get all the correction data, or you can get all the positioning signals, and then the software will do the uh, position computation here using the Madoka correction data, and you get the output here. And this gives you a 10 to 20 centimeter accuracy. But many people don't have this Madoka processor. Okay? So if you don't have this Madoka receiver, this one, you can still do the Madoka by using getting the Madoka correction data through internet. You can access our server and you can get the correction data. So as long as you have a dual frequency GNSS receiver, you can use a Madoka as well. But you need to access through our server. Okay? So there are two ways of doing it. If you have a GNSS and Madoka decoder, so only this hardware is enough. Okay. If you have only GNSS dual frequency receiver, then you access the Madoka through our server and you do the Madoka PPP. You just need the internet access. Okay. Then without the base station in India, you can have a 10, 20 centimeter of accuracy wherever you do the survey. In the sea, in the land, it doesn't matter. If you are going to use RTK in the sea, it's very difficult because you don't have a base station within 30, 40 kilometer in the sea. Okay, it's not possible. But in the sea, you may not need the accuracy of 10, 20 centimeter. So that's another issue, whether you need or not. And this is the same thing. Okay, I'll skip. So this is our receiver for Madoka. And these are some screenshots of Madoka, RTK droid, Mod droid. Okay, you can see where is the accuracy value here. Latitude and longitude error. Okay, so but it will take some time, 10 minutes or more, to have a 10 centimeter of accuracy. So once you have this convergence for 10 centimeter accuracy, then you can move. So this is the only thing that you have to do. You have to wait initially for about 10 minutes, and then you can move in Madoka. But in RTK, I think it's just a matter of 1 or 2 minutes. So you get a fix, and then you can move. And these are our graphics interface. So we made it very simple. So you don't have to remember any technical things, any other commands, and so on. Any person who even doesn't know what is GNSS can operate it. So this was the purpose. You just We just need to give maybe half an hour, 1 hour, just instructions or training, and that's all. So you just need to connect the cables and then select which one. You need to know which one to be selected. And once you select everything, and then you press the start button, and it will start working. Yeah. In the beginning, you see the error is very bad. It will take some time to converge to the centimeter level. So as time passes by, it will go to the centimeter level of accuracy, and you can see here how much is the error. Okay. And this is the same for the Android version. And these are just a comparison how the Madwin, MadPy, and Madroid works, and for what type of receivers, or what type of receiver, or what type of data format we can use. But this is not very important because it keeps on changing. So this is just for our purpose. So it's not very important. The only thing is that we have 3 platforms. One is Windows, Raspberry Pi, and Android. These are some snapshots. So after running for some time, you see the errors getting reduced and reduced. And it also records the raw data. So it records the solution, means the Madoka PPP computed solution. So these are the actual outputs. But if you want to do post-processing, we log both the rover raw data and the correction data coming from the satellite or internet. So you have this rover data. So once you have rover data, you can also do the RTK, the raw data. Okay, this is the raw data, and you can use this data to do the RTK post processing, okay, or PPK post processing kinematic. You just need to have a nearby base station data, and you do the kinematic processing using this raw data. Okay. As if you observe for a very long time, so the error gets minimized, smaller and smaller. Okay. And these are the actual screenshot of the Mat Pi, the Raspberry Pi. So this is how it looks like. Okay. So a small Sky Plus, CN0, and some status here. And this is the actual device. And now we are exploring whether we can also do space weather. Okay, but space weather requirements are a bit different. So we are just exploring at the moment. We don't know whether we can or we cannot. But at least for TEC, it's more than enough. For TEC, it's okay. F9P or these type of low cost receivers are okay. So we are going to test with this type of receiver. This is actually F9P from UBlocks, and this is the Septentrium Mosaic module. So it's a bit expensive. So this is about 700 euros. This is, I think, $200 or $300. Okay, but this has a bit better output. So it can output raw data up to at 50 hertz, and also maybe special output at 100 hertz only for measurement, but we can't use this for RTK. But it has, yes, better performance. That's why it's a bit expensive, and also it has additional signal, three frequency, yeah, the Mosaic. But this one is only two frequency. So now we are going to explore that whether it's possible to use for space weather, basically for TEC and S4. TEC definitely, I think it's yes, but S4 we need to explore, and we are also contacting the manufacturer maker directly to know whether they can help to make it space weather compatible. If it is not possible at the moment, okay, we are also talking with them directly. And these are the, yes, F9P, but we customize the board to log the data using the ESP32. So you can customize everything, integrate everything, and make it very compact as a data logger. So many things can be done. And some results of the TEC computation using this low cost. Sorry, this is not the low cost. I don't remember which data we use actually. Um, I need to check which data. Actually, we want to do it a low cost, but we need the software. Okay, and we have some software, Flurry, and this is Gopi from one guy in India. So he provided a binary, but we don't have a source code. So only the binary executive file, and with only the executable. So it's not much we can do. So if there's some error, we really don't know what happened. So then everything stops. Okay. But for Flurry, we have a source code, and I'm now modifying this source code to make it compatible with the low-cost receiver system. So lots of work to be done here. And also in a quick model, this software is available, and we can also use this one for high-end and the low cost. Okay, and the last one is this Expressense product. So this is another new board, new device. So this is actually the main board. So here is it's from Sony. So this board, this device has a GNSS receiver as well. It has a very nice CPU. I think 6-core CPU, and GNSS receiver. This is a small GNSS chip antenna here, and it can receive GPS, QGIS, GLONASS, and Galileo, I think. And this also can be attached to extension board if you need more different types of interface and other some controllers here. And SD card is here, okay. And then you can attach a camera, or camera you can attach to this board itself directly. So different types of camera, so you can attach a camera here. The good thing of this board is that it has uh, NNC, okay, a neural network console. And for example, you attach a camera here and you take some image. And if you want to do AI or some data analysis or neural network, all these type of advanced data processing, this is powerful. It has already the API engine already there, and you just need to call them to do your data analysis or AI like data processing or neural network data processing. It already has built-in features. So this is what I like, and the cost is about $50-$60 in internet. I think you can. I don't know whether you can buy online in India, but anyway, it's not that expensive. But it's quite powerful as well in terms of the CPU. But in terms of the GPS, it's only single frequency, not so good. I mean, powerful like UBlocks L1 single band for GPS, but it's much better as a whole. Okay, this may be another choice of device for some of the applications that you are planning to do. And you can see the engines, or I mean the architecture here. Here you see the CPU, 1 to 6 core CPU, and you can individually program them, control them, and lots of different types of interfaces here. Okay, and the camera interface, GNSS, and it's more for the audio channel, 8 channel. That's a use. Okay, the Sony is quite good in this type of audio video systems. And you can use Natyux programming language, or you can use even the what else? Let me see. Arduino, okay, Arduino. Oh no, this is audio, but also it has. You can use Arduino. Yeah, and here for the data analysis, you have TensorFlow and NNC, and it can be integrated with IoT protocols, okay, and many different things. So it's very powerful. And it has a very nice tutorial. It's very well documented in English. So I really like this type of tutorial. You have a YouTube videos, you have all the source code and example codes, and it explains in very detail. So it's a perfect material for learning. You can see the Arduino compatibility ports here, okay, with the Arduino and other things. So you can see this interface and you can connect the wires or make your own interface as you need it. Okay, so that's all from my side for this one. I will skip this Android. So just download and log the data. I think you have other training materials probably on this. So just refer this. And I have logged some data to show you how good. And I'm using Xiaomi Mi 11 Lite 5G. I think if you have this version in India, it can also acquire the Navic signal. Of course, yeah, you see this is L5. Yeah. So probably you need to explore some Xiaomi new version. I don't know which one is capable of what, but at least this one can receive some Navic as well. Okay. And it outputs the raw data. This is L1, L5 compatible. You can see you can output Rhinex data as well if you select to output it. Some screenshots, and it has a different way of computing the position data. Okay, and here you can see all the visible satellites. And these are some examples of our low-cost V system development. Used our receiver system by the University of Philippines to measure the water rise level. And this is our master thesis project last year, done by one student in Nepal, low-cost dynamic air quality monitoring, because before the COVID, so it was the air pollution was so bad that you hardly see this type of clear mountains. So you see this is the same view. And during the COVID, when no vehicles on the street, is so beautiful. So you can see how much the air quality changes. Then we had idea why don't we measure the pollution here. Then we purchased very low cost this type of air quality monitoring sensors and integrated everything into this box with this M8Q receiver. That's just I think $30 board, and put everything house and then log the data. Driving around the city in a bike or bicycle. So and then did some analysis. It's not that good to for the I mean data. We We need to improve the data analysis part, data processing part, because of other effects from the sensors itself, like this device gets hot and our PSD sensor, temperature sensor, is not measuring the air temperature anymore. It's measuring the device temperature now. So we need to modify our design itself to remove these sensors from outside the box to the side or somewhere else, so that it's not affected by the temperature of the device itself. Yeah, but it's quite good. Okay, this is just a prototype that how such a low cost system can be used for very complex measurement observation. And this data itself, you can use for air quality, you can use for traffic congestion monitoring, you can use for drivers behavior monitoring, and so many things. Okay, we have accelerometer, gyro, and we have different types of gas sensors. Okay, we could not even at the moment we have not yet done the calibrations, but one if you do this some sort of calibration, it gives you a very nice data. Okay, that's all. So I would like to stop here for this part, and I would like to have few comments or questions from you before
Okay,
I go
so
to another one.
thank you, thank you, Dr. Manandhar. And now you have any question on the first part, because in the second part, Dr. Manandhar would be covering the. I have requested him to talk about the spoofing. That's a very interesting thing. So if, to stop here, please, if you have any questions. So already one question is there, and if you have any question, just open up your microphone and throw your question. So already one question is here. Somnath has asked about update after update Madoka compact SSR software from India. We will check Madoka PPP system performance and let you know. Okay. And Shukabo also has raised his hand. So first Somnath's question, then Shukabo, please ask the question. Dinesh, please. Hello.
Are you calling me, or who
Yes,
is?
yes. No, Somnath has commented that he wants to know when the
Yeah, of
updated.
course, yes, that will do, yes.
Okay,
But
okay.
what was, yeah, what
Now
was the
Shukabo, please.
question from Sukava? Yeah.
Shukabo, please. Shukabo, please. You can ask the question.
Hello.
Yes, please.
Yeah. Very good evening. The question is, what are the parameters you are looking to study the compatibility of the low-cost GNSS receiver for S4 studies?
For what studies? Sorry, I could
Uh,
not.
Sir, you have
Probably
shown one slide now for S4 and take calculation study. Yeah.
S4,
space weather monitoring. For
space weather.
So what are the, his question is, what are the parameters you are interested of?
For space weather, okay. Let me share
Yes,
you this. Can you see my slide now?
it has just come.
Okay. Can you see now the slide?
Yes,
Yes,
yes.
sir.
For
Yes, sir.
okay. So we are targeting TEC and S4 computation. Okay. For S4, as far as I understand, I need I and Q channel power. Okay. This is what I understand. But I I see some papers, they are computing S4 from CN0 or SNR.
Mm.
But I'm not satisfied with that. However, I'm not an expert in space weather, because my understanding and my logic tells me that I need power of the I and Q channel. That means the when we process the GNSS signal, we have a tracking output of I and Q channel, and I need the power of the signal and the noise. And from there, I can compute the S4. But the receiver, normal receiver doesn't output I and Q power outputs. It's a lot of computation and memory required. So standard receiver just output SNR, and there are people computing S4 using the SNR, and very surprised how that can be possible. So this is a question from me to the experts in the space weather. Can you compute S4 using the SNR or CN0 values? If any of you are doing space weather, so please teach me how to compute S4 using SNR, or is it possible? Or should we do that? Is this a correct way of doing this? Because I even see some papers published using SNR value to compute S4. And for me, that's completely wrong. So for the space weather low cost, we are looking the raw data output capacity of the receivers. If the raw data, you see here, if they can output this data, then we can use it. But for S4, we need the I and Q power output. Okay, these are our parameters that we are looking. And we need at a very high rate, maybe 100 hertz, not just the 10 hertz or 20 hertz, not even 50 hertz. But I think 50 hertz is more than enough. But I would like to have it at as high as possible. Okay. And September said they can output at 100 hertz. They already mentioned in their spec. So that's why I'm selecting this receiver. Okay. But I'm still not sure whether it's still possible to compute S4 using this device. So I'm asking September itself, let me know whether your device can do this. And they are still consulting their engineer. So I don't know whether we can do with the SNR. I don't think so. But I see the papers already published.
And sir, is there any provision to get the I and Q channel power from general
No,
purpose
impossible.
690?
No, impossible.
Oh, okay.
Actually, what we get, what I understand, I'm also not an expert here, but from other speakers and also from different sources, what I found that when we calculate the S4 using C by NO or by SNR, what it gives us, it's the equivalent S4. Not the exact S4, but
Yeah,
what they
but
call
what does that mean? Equivalent S4. So
No,
is
so
that
they
useful
put it
or
that
not?
way.
If that is
That put it
useful,
that way.
life is very simple. Okay. So equivalent means, what does it mean?
They tell it equivalent is for what I have also found. Uh, Okay, so I have two questions. Before there is another question typed by Dr. Adebayo from Nigeria. There are two questions. First question is how good is the GPS chips performance in Espressens, Sony Espressens? That is number one. So
Sorry, what was the number one question?
how good is the performance of the Sony Espressens module? It is GPS single frequency, GPS L1 only. So how it is performing in
So
comparison
that
to
is the standard GPS, okay? Standard point positioning. So that means it will give you a accuracy at the standard level. That's a 10 meter.
Okay. And the chip, what they use, it's Sony's own chip or somebody else's chip they use on their board?
No, it's a Sony, okay?
Okay. That is number one. Second question is, we have developed similar thing, but you have already mentioned that dynamic air quality monitoring. So also in our case, we could not calibrate it. So can you give us some light that what would be the best way to calibrate it? In our case, it only measures the PM 2.5, TN10, then the temperature, humidity, pressure. We have not integrated the gyroscope and also our accelerometer or the gas sensors. But what may be a good way to calibrate it? We have not till now also calibrated.
When I say calibration means to calibrate each individual sensor Basically, it's the environmental sensors, okay? Like a
Okay.
PM2 point, PM1, PM2.5, or 10, or 100. So to
Mhm.
calibrate those sensors itself, like if PM2.5 gives some value, but how to calibrate that value, okay? So probably you need to have some offset or something like that, that you need to do. And in order to do that, you need maybe some standard device itself, so side by side, which is already trusted by the users or some certified by the makers. So they probably provide you a certificate that this device is already calibrated and the readings you get is it matches with the standard values. Okay, I mean units and all. But in our case, like not for the PM 2.5, but for the let me show you for the gas sensors like a CO
Mhm.
or NO,
Mhm.
N2O, those
Mhm.
things, it doesn't output the values itself. It's just some number. So we need to change from those numbers to some meaningful values. Okay,
Okay. Okay.
like you
Okay.
have a 16-bit register, and that values will be something like 15,000, 16,000, and what does how to interpret this 15,000 to something micrometer per something meter square, okay,
Okay.
molecules per meter square or
Okay.
something like that, that we need to do. That's the
Okay.
calibration
Very,
for the
very
environmental
similar
sensor.
to the very low cost soil humidity meters.
Yeah,
Uh,
yeah,
these,
something like that. Yeah,
they only give some
yeah,
numbers, not in
yeah,
terms
they
of.
output just some values, and then you
Yeah.
have to convert from those values to the meaningful units. You need to provide the units. Okay.
So what we did in that case, we took Shukabu has done it. So we took a few samples of soil. So it's completely dry, then very little moisture, then a bit moist, then fully moist, then flooded. So we took some 5 categories, and for each categories we tried to find out the values over a long period of time and take the average. That way we did it. In
Okay.
case of that soil moisture meter.
Mhm. Yeah.
Okay, so there is another question from Dr. Adebayo. Uh, how can we synchronize weather measuring device data with the RTK data in a situation where the RTK cannot measure both data?
Mhm. So the
Uh,
question is simply how to synchronize the two data, okay? I
mhm,
mean, with respect to position and time.
mhm.
So is this the question? For example, you are observing the position data using the receiver, and you are also observing the weather data, okay, using so many different types of sensors.
Probably, I think that is the question. Adebayo, can you open up and ask the question yourself? Adebayo, can you open up your microphone and ask the question directly, please? I think he became offline maybe due to network issue. So maybe
Yeah,
afterwards.
basically the question is how to synchronize the time, I mean the sensor data,
Mhm.
environmental sensor data with the GPS data. Okay, because some sensors they output at 100 hertz or 50 hertz, but GPS data output is at 1 hertz. So you have only one output every second. But other sensors you have maybe 10 outputs every second. But some sensor data just one output for every 10 seconds. Okay, it is at 10 hertz or it is at zero point 0.1 hertz or zero point 0.5 hertz, something like that. But we must time tag every output from the environmental sensors. And this we did by using the GPS time. So we have this GPS time synchronization logic built in our system. So you can, so they are all time tag within the accuracy of a millisecond. So this we have done it. And many people, they don't do it. They can't do it unless you have a good knowledge of how to do the time sync using the clock of the GPS, and then you feed into the clock of the some of these sensors boards. That's a bit difficult and tricky part. So that's the main thing. But in
Okay.
our case, we
Uh,
have the time sync here, clock sync here. Not the clock sync, the time sync of the different sensors do the same, and the accuracy is within the millisecond level.
oh, that's great. That's great. Can you hear me
No,
now?
that has to be done. Otherwise, it's not useful. Okay. In the dynamic,
Oh,
in the static, you don't need it, but in the dynamic, you must have it. Otherwise, the data you are like we are driving here, and how do I know that this environment data is taken at this point? It's impossible. Okay, in the
yeah,
dynamic mode.
yeah, yeah. Okay, that means that will be done in a kind of static mode.
No, no, no. It's in the should be in dynamic.
Okay, it should be in
Once it's
dynamic.
done for dynamic, it's valid for both static and dynamic. It doesn't make any sense. But if you are not moving, you don't have to do the time tag.
Okay, okay.
I mean, you need to do, but very simple time sync is okay. Within a second is okay because the environment data doesn't change within a few seconds. Okay.
Yeah, yeah, yeah. Thank you. There's still one other question I want to put forward. Can I go ahead?
Yes.
Okay. Now, while you were talking about the rover and the base station, so I pick an interest in that. You said about 30-kilometer distance between the base station and the receiver station. Now, in case of a situation where you can't even extend the distance beyond 30 kilometers, by the time you have taken the reading, will the accuracy be affected? Take, for instance, in a city where you have high-rise building and a kind of cluster settlement where you cannot actually put the receiver and the base station at a distance that is as wide as 30 kilometers because of multipath. So if you reduce the distance lesser than 30 kilometers, let's say 10 kilometers apart, will that really have significant effect on the accuracy?
The longer the distance, the worse the accuracy. Okay. So
Okay.
if you look at the specification of any this type of GNSS receiver that's designed for RTK, you will see their specification. It says, for example, 5 centimeter plus 1 ppm. So this 1
Okay.
ppm will tell you how much accuracy it degrades for every kilometer. Okay.
Oh, that's great. That's
So
great.
if you go from 30 to, you can do RTK even for 100 kilometer. Okay, but
Oh,
for I think every 10 kilometer, you will add about 1 centimeter of additional error.
error.
So if you
Every
go to
10
100
kilometers.
kilometer, you will have at least 10 centimeter of
10
additional error.
centimeters.
But I don't think it goes linearly. Okay, so this
Okay.
linear is not valid. So at the 40 kilometer, you will have about 4 centimeter of error coming due to the length of the base length. Okay, because the
Okay.
base length is about 40 kilometer between the base and the rover. So if the receiver spec says 1 ppm, you will have at least 4 centimeter of error. And plus you have the measurement error of, say, if it says 5 centimeter, then your RTK will be accurate within 5 and 4, 9 centimeter. Okay? So you
All right.
can't get better than 9 centimeter. And if you are looking for 5 centimeter of accuracy, then your base length must be within 10 to 20 kilometer.
Okay. All right.
Okay?
All
Don't
right.
expect than what the spec says. And when they say 5 centimeter, and they are very tricky, they may be saying plus minus 510 centimeter, plus minus
Okay.
5 centimeter. Okay. I mean, when
Okay.
they say 5 centimeter, it may be plus and minus 5 centimeter, and that's equivalent to 10 centimeter now, because it varies from minus 5 to plus 5. So the range is 10 centimeter. So your accuracy can be guaranteed within 10 centimeter only, not 5 centimeter.
All right.
So
All
the
right.
makers are very clever to show you a smaller figure, and they sometimes hide those important signs.
Okay.
And
Thank
that
you very
also
much.
the probability is only 50 to 60%. So and they, if they don't say anything, so take it as a 1 sigma, not 2 or 3 sigma. It's impossible.
Okay.
Yeah.
Thank you. Thank you. Thank you.
Okay,
Okay,
thank you.
so we'll go to the next part. Otherwise, we'll be short of time.
Yes,
Uh,
but when you change, let me tell a few things to the participants. So thank you very much, Dinesh, for setting up the platform on which we will start our offline program next week. So you can see not only, so over this week you learned about GNSS, how it works, what are the philosophies, what are the principles. And next week onwards, we will be working on how to develop what are the use cases of different applications that can be generated through GNSS. That's why it's meant for. So thank you very much. So today evening you have set the platform, giving many examples, many interesting examples on which our participants may work on. So please, the next slide, please.
Okay. So for the next slide, I have some videos. Hello, Anindya.
Yes.
So for the next
It is.
presentation, I have some
Mhm.
videos, but these videos you can watch, but you can't record, you can't distribute. Okay. I suppose
So
that you are going to
should
distribute the
I
recording.
stop the recording? I would stop the recording then.
Yes, because these videos cannot be distributed. You can watch.